Before I get into it, since some of the people on this are in San Francisco, we have the summit for Apache Pulsars at the Hotel Nico on August 18th. There's going to be, besides Pulsar, a lot of other people from the data community there, from Google, Amazon, OneHouse, Startree. You could see here a lot of different cool technologies. We got a code to get you a discount there if you're interested in attending. David and I will be there, as well as the major committers. So it'll be a pretty cool event. We're still talking to other communities. So if you're in an open source project or in some other data community, you want to reach out. We have different sponsorships out there, and we have free ones for the open source communities there, just to co-promote and such in a live event in a couple of weeks. Every week I send out a newsletter, try to cover most of the topics in big data, streaming, open source projects, Flink, Pulsar, NiFi, and Spark. I run this through LinkedIn. Pretty easy to join, and you just get one link a week with videos, content, demos, different things. So we're going to cover streaming data pipelines, easy way. In theory, we'll have a live coding demonstration. I posted all the source code, so if it doesn't work, try it yourself. You can scan this if you want to go there right away, not have to type anything. It's pretty easy to get to the code. The demo.
And we will post these slides and recording on our meetup page. So for those interested, we'll definitely post this.
Very cool. And our example code is, I've got a sensor running almost on screen. I guess maybe you can see it. This little guy. Hope I didn't break my server picking it up. We'll see what happens. So that sensor is sending bunch of different readings for temperature, humidity, carbon dioxide levels. So if I'm breathing on it, we'll see what happens if I mess it up, make it too hot. That sends sensor data via a Python application into a Pulsar cluster. Pulsar cluster, it has a sink in it. We configure that with some YAML to push that data into Delta Lake. Then we're going to take a look at that data via simple Spark app. That same Spark app could also talk directly to Pulsar if we wanted. And I've got a little Flink app that's doing some continuous SQL against that data as well, just to show you, we could have batch data, we could have real-time data. You don't need different systems to do it, don't need different languages. Pretty simple to do all this without a lot of overhead or extra layers in there. It doesn't matter where it's running. But what is Pulsar? It does messaging and event streaming. It's all in one. What's kind of cool is, since it's pretty recent, it is cloud native from design. So it has compute and storage separate, so they could be spun up independently. And we've got in the open source the K8 operator and Helm charts out there. So pretty easy to set up your own cluster without having to do heavy lifting. Get one platform to do any kind of messaging and streaming. We guarantee those messages get delivered with some serious infrastructure behind that to make sure that happens. System itself is very resilient, designed to survive some pretty catastrophic failures. You could lose servers, you'd lose segments of data and still run without losing data. And the scalability is not limited by anything other than your amount of money you can afford. There are some pretty large implementations in Asia where they're getting petabytes of data, and it scales out to hundreds and hundreds of nodes, hundreds of thousands of topics, lots of data. Why do people like Pulsar besides the cool logo? Out of the box multi-tenancy. You don't have to buy some kind of paid add-on. All this is in the open source. So I could have multiple organizations using one cluster. Again, that scalability and be able to scale storage and compute separately. Geo-replication built in. Don't need to write any code. Set up some configuration and decide how you want data replicated to different clouds or different availability zones. One messaging model for any type of messaging or streaming, and that really strict data durability. Make sure we don't lose your data, store as much as you want, and automatically tier that out into cheaper object storage when you get to some idea. So those are some of the advantages of Pulsar over Kafka: the built-in multi-tenancy, the built-in geo-replication, being able to support messaging, which is not the same thing as streaming. Messaging, typically things like RabbitMQ, ActiveMQ, and we support that style of work queue, messaging that doesn't have to be in order, messaging with some more complex subscription types, and the ability to support other protocols, such as MQTT, such as AMQP, which is used for Rabbit, and Kafka's protocol as well. Simple API to use, very easy to get your data in and out, and to use it, like I said, for messaging and also streaming like you would do in Kafka, but with that built-in multi-tenancy and the separation of compute and storage. If you know Kafka, you've got a Kafka broker, it's got the storage and the compute and everything is in that one node. So when you have to scale up, you're adding this big node, probably has a big SSD disk. That's not the case with Pulsar. If I want more compute, add another node. Nodes can be a lot smaller. Very easy to dynamically do that with Kubernetes, which is in the open source. And the storage is handled by a real data engine. It's done by Apache Bookkeeper, which runs more like a database than just a simple log file. So supports for writing faster and more scalable. And David could get into that later when we get into messages if you're really curious about that one. Good architecture for this, like I mentioned, stateless compute's done by Pulsar that has a little cache in there. The bookkeeper handles message and the subscription state. So as opposed to Kafka, you don't have to handle this in your code where you are in a subscription to your data. The server will store that for you. So if you lose your connection, come back in, you're not trying to figure out where you were. Pluggable metadata store, that could be etcd, could be RocksDB, could be Zookeeper, manages that metadata that's needed for keeping track of what's going on and some service discovery. Easy to scale these independently. And if you're running Kubernetes, you probably have etcd already, and you can use that for your metadata. Little deeper into that. Pulsar is doing that routing of messages. So with some cache, but stateless. So very easy to scale those out, have them scale down, auto load balancing within there. Topics are built into segments, makes it easy to spin things up quickly and scale out. Again, thousands of topics without a problem. And because we have that multi-tenancy, we break things up into tenants, namespaces, and topics. So it gives you a hierarchy, makes it easier for you to secure and organize your topics. Again, a little different from Kafka. What's also cool, that unified model, doesn't matter what protocol of those producers to get your data into the system. So it could be Pulsar, could be Kafka, could be AMQP, could be MQTT, could be WebSockets, could be REST. You get those data into Pulsar, and it how you consume it decides if it's a streaming app or if it's a messaging app, which gives you a lot of flexibility and lets you decide, when you're consuming data, what type of application you're doing. Are you doing a failover app where this is like streaming, like Kafka, exactly once in order, but if something goes wrong, let someone else take over for you? If you want to divide who's consuming your data, sort of like consumer groups, we could do that with keys shared. If you want to do a work queue or traditional messaging, do shared, and then whoever gets the next message, they get it. So you could process things really quickly if you don't care about ordering, which is, again, a type of messaging. Pretty easy idea here. Producers get the message into a topic, gets into a broker, Broker makes sure it's stored. And then it gives an acknowledgement back to the topic that it's not lost. Messages are any type of payload you want. Under the covers, it's just raw bytes, binary data, but then you could define on top of it what type of data it is. We've got a built-in schema registry if you want to use schema to define your data, whether it's JSON, Avro, protobuf, what have you. Subscriptions let consumers point to what data they want and get that in the way that they want it. Makes that nice decoupling there. Pretty easy to do. We have that join. If you have more top questions and you don't want to put them in that chat, we've got a Slack channel. Topics, like I mentioned, for that hierarchy. We've got tenants, which can span clusters, and we've got namespaces under those tenants. So this makes it really nice if maybe you have multiple companies on one cluster, or you're sharing resources between different groups. Very easy to organize where your data is going to go, which is nice. I'll go through the terminology and then getting close to handoff with David, and he'll do some more slides, and then I can do that demo. Hopefully the demo gods are with us today. I brought the lucky rabbit here. I think we've covered most of these terms. Again, you'll get these slides. Anything a little weird here? No, I think we've got all these. David, you want to cover some of these here?
Sure, absolutely. Thank you, Tim. Thank you for that great introduction to Pulsar. Yeah, we saw some questions about how it compares to Apache Kafka. Obviously, that's a question we get a lot. Just to give some additional background, Tim and I, in our former lives before Stream Native, shared some time at Hortonworks together, where they were a big purveyor of Apache NiFi and Apache Kafka. That was sort of their get data end model into Hadoop clusters. And he and I both saw some of the fundamental issues and flaws in that architecture. So we decided to switch over to, Pulsar, and became really big advocates of that for scalability and resiliency and all these different features that he talked about as well. But obviously Kafka has a big presence, right? Everybody knows Kafka. People who've gotten into the streaming case early, including, our clients from 5-6 years ago at Hortonworks and Confluent and others, are obviously dealing with this Kafka code. And there's a lot of legacy code out there. So one of the things we first wanted to leverage was a pluggable protocol capability that's inside of Apache Pulsar, right? So it can speak in addition to its own binary protocol. We've made it such that it can talk to Kafka clusters. It can talk to AMQP clusters. So if you have an existing RabbitMQ cluster and want to integrate with that, and you can switch things over, so you can basically take your existing source code with things like Kafka and point it to a Pulsar cluster that's enabled this Kafka on Pulsar native protocol handler, and have it act transparently as if it were a Kafka broker. So you get all the architectural benefits of Kafka without having to rewrite your entire code base just because you switched your underlying architecture. So we found this to be a key differentiator on that, and that's what this slide speaks to. You can have existing code on both. You can commingle data published by Pulsar producers with Kafka producers as well, and so it can scale out in multiple different ways. So it's a highly flexible, first truly messaging system that supports different messaging protocols. They all, up to this point, have picked one and stuck with it. AMQP is sort of a standard that RabbitMQ and these other active MQs sort of use. Obviously, Kafka built their own, and then Pulsar has its own, but they all support these things. And so this is showing, again, this is another example of this with the MQTT protocol, which is another flexible, obviously, for IoT space, for sensors, things like that. So it's a very lower level transmission protocol. You could deploy Pulsar brokers out on these edge devices because it's completely decoupled storage from compute. So you can put a broker out on an edge device and have it talk directly native MQTT to other services and get that data in there that much quicker, and do some processing on that as well. And they all follow the same pattern. Of this slide here is talking to the AMQP. So again, if you have existing RabbitMQ libraries and you want to take that code and it's legacy code and you want to bring it over without having to change it, we can do that very easily with a Pulsar as well, using this protocol handler. More in the pipeline. There's a JMS one, there's additional ones. So it's a very flexible protocol, and allows us to do these different interfacing with different systems as well. Does it also work well with IBM MQ? It depends on what protocol IBM MQ does. It's really down to how we send the bytes over the wire is what we're really manipulating at this point. So we make sure that the message bundles match what the clients are expecting when they crack open those messages we send over those raw bytes. and they can interpret that. So that's really, but if there's a different protocol, we can easily write something for like IBM MQ. Absolutely. We also support different, styles of IO connectors. So included in the Pulsar framework is this, or with the Pulsar library itself, is this framework called Pulsar Functions. It's a lightweight computing system that acts similar to AWS Lambda. Those of you familiar with AWS Lambdas are these serverless function as a service sort of capabilities out there. You just write the code, you submit it to the platform, and it executes automatically, and all the wiring happens under the covers. As part of that, we have an IO connectors, which is an extension of that to get data into and out of Pulsar from different existing systems. In this example, showing AWS SQS, you can bridge it in. We can take data from an existing system into Pulsar to do analytics on it, for example. You can take data from Google Club, Pub Sub. You can do it from additional databases, Cassandra. We have Debezium, so you can do CDC capture into Pulsar. It's a really extensible framework. There's a lot of IO connectors out there as well. And then we can leverage that, the functions framework for things like machine learning as well, things like that. And I think Tim might get into that in the slide in these talks. So yeah, this is basically saying we have lots of ways of getting data in and out of Pulsar from existing systems. It is a nice bridge as well.
I was going to say, if you want to go a little deeper, I did go through the architecture slides a little quickly. If you want to put some insight in here to differentiate between Kafka and give some more of those advantages.
Sure.
At the architecture level.
Absolutely. And thank you for this, Tim. Definitely one of the things that I kind of mentioned in the Slack was, okay, the stateless brokers allow us to have two things right away, and that is a zero uptime, a recovery of a broker. If a broker dies, we can immediately spin up a new one, and we don't have to preload the data as you do in Kafka, as you mentioned, right? The data, the benefit of the purported benefit of the Kafka broker storing the data locally is that there's one less network hop, so it's more efficient. And that's an architectural trade-off. I won't argue with that point. Going to local disk is faster than going over the network to get some data as well. But we feel that the cost of having the separate storage layer gives us a lot more benefits. One of them being, again, an immediate recovery, resiliency in the framework. If a broker goes down, immediately another broker can take over because the data is stored in a separate layer. All it needs to do is go to this metadata storage and say, okay, I'm trying to serve messages from topic A. Where's this data in Bookkeeper? Boom, it'll point it to you. You just make a network connection over a local network hop. You get that information and you can immediately recover. So we think that benefit outweighs the performance hit, that minor performance hit that you're taking. Another benefit is this that fifth bullet point there, automatic load balancing for the brokers, right? That is a way. So again, if you can get things like hotspotting, you have one or two very busy topics and you have a lot of consumers and clients coming in and talking to that, and that particular broker becomes a hotspot. The other brokers aren't really doing much, but this one or two brokers are really getting saturated with network connections. By being stateless, what we can do is crack these, basically split these bundles, these topics over, and reassign them to other brokers in real time. And so we can dynamically balance the load of this data and automatically spread it out across different brokers to get full throughput, right? So you're not getting one or two brokers doing all the work, another one sitting idle. We actually get full network saturation, full utilization of your broker layer. So it again becomes more cost effective to do these sorts of things. Another benefit is that I always didn't like about Kafka was the partition. You have to add a partition in two different situations, primarily when you wanted to scale up storage beyond the capability of a capacity of a topic, right? You want to keep data around, you want to keep, 5 terabytes of data or 100 terabytes of data. Your only way to do it was just to add more partitions so that you had enough disk across these brokers to handle it. There is no such limitation for storage on topics in Pulsar. You could have a single partition topic in Pulsar that could store a petabyte of data. It does not matter because of this separated architecture. So a lot of people would struggle with, okay, I got to repartition my topics. Whenever you do that, there's a stop the world moment. You have to rebalance and reshuffle all your data from where it was stored on 4 partitions to 5 or 6 or whatever you went up to. There is no such halt the world scenario in Pulsar. You just basically add another metadata segment to your broker, to the metadata storage, to say I'm adding this particular ledger, which is what we call this in Bookkeeper. I'm just adding more data, and you can expand infinitely without having to ever really worry about partitions. As a committer, I kind of have access to this, but we're going to be adding the case where in the very near future, where partitions will be this, we do support partition topics. And the only reason we use that is the second reason that you would do it in Kafka, which is to span out the load across the brokers, right? So you really know you have 500, you have 5,000 consumers of this topic. One broker just can't handle that from a NIC card perspective. It becomes a physical architectural limitation. So you want to fan out. That's the true case for only you should partition. We support that in Pulsar by default. And we're adding this capability to automatically detect that scenario and add partitions for you dynamically. So you never have to worry about partitions. You only focus on, topics, structuring of your data. Pulsar is going to handle making sure it's always available for you, always doing the maximum throughput, and partitioning for you automatically. So again, it's another way of handling this information. So I think those are some of the benefits. I mentioned cloud native is another one, as you mentioned. So bookies are the same way. You can scale them up immediately, add more storage. There is no need to add a broker layer on top of that. So there's just a lot of advantages to that. So yeah, thank you for that. How do you split the topic? Great question. So actually what we use was what called, if you go to that slide about namespaces, we could use what's called namespace bundles. And so you split these bundles using a hash ring. And so every partial, so obviously topics sit underneath namespaces. So we split these namespaces by default into a number of what we call bundles. And then you're assigned a bundle, an entire bundle is assigned to a broker. Now, let's say under this campaign's namespace, for example, that Tim's hovering on, there are 1,000 topics. That's okay. We split it by default, let's say into 4, which is the default setting. So there's 250 topics in each bundle. As bad luck would have it, one of those brokers that gets the bundle with 250 has all the traffic going to it. So it becomes very saturated. And we track information, the metrics on a bundle level rather than a topic level. So it's more, we don't have to worry about the granularity. So it makes it more efficient. We decide, okay, this bundle with 250 topics is now using too much load and we want to get rid of it. We want to shed some of this load and reassign it. So what we do is split that bundle in half. We take that hash ring and we split it and say, okay, now there's 120. We create a brand new bundle and say there's 125 here and 125 in this hash range. And we take we keep one of those on that broker and we toss the other one, the 125 back to a broker pool to get reassigned. That will land on a different broker. And then it will take over serving those 125 topics. And then every minute we do this, this balancing as well. So again, if that wasn't right and we need to split it again, it will happen again and again and again until you get the proper number of bundles so that the load is evenly distributed across all the brokers. And, there's a certain threshold at which that's triggered, but it does this automatically for you. And it just splits it by cutting, basically doing a hash range and splitting it in half. Yeah, great question on that. So
What about the segments underneath the topic?
yeah, that's a great question. If we had a slide that shows, so in Bookkeeper, what it does is a segment-based storage rather than an append log-only storage that you do in Kafka, right? So what we do we have a picture of this? Probably not. But you basically start, you can, in Kafka, you can think of it as one large log file, right? You're writing a log, you open up your particular partition, that topic, and you start writing and appending to the end of that file. And once that file is full, that's it. You close it down. That's it. So the entire block of data is co-located on this local disk. Now with Bookkeeper, we do it separately. We periodically break that up into what we call segments, right? So every 50,000 messages by default, we stop and say, this is a segment, right? We have 3 open segments. They're all written concurrently to 3 different bookies. And that way they're scattered across all these different bookie nodes simultaneously, right? So that gives us the geo-replication or the replication redundancy that you need for the data to be on the local cluster to be available. But the added benefit is when you want to go back and do tailing reads. So again, you want to do like historical reads and I want to point something like Flink at it, like Tim's going to do, or Spark. You can take a separate IO path and read that data directly from different bookies because the data is stored in segments across different nodes. So you can get the full effect, the full IO throughput of all these machines rather than being pinned to one if you're reading from a topic, right? So again, if you're reading from a single topic and reading the most recent data, you have your head pointer at the top of the broker, and any sort of caching on that topic is kept there. But it's one machine, it's one IO path. That's all you can do with the Bookkeeper by having it spread out in multiple segments. If I'm doing a historical one, I can say, hey, this is on Bookie 5 and go read the data from that IO disk and use that IO controller to get that information, while at the same time read something out of Bookie 2 to get more recent information. And the third one, the broker could be serving out of local cache the most recent data. So we really fan out the IO throughput to make sure there is no bottleneck in the system, which is what allowed us to get up to 10 petabytes worth of data being pushed through a system at Splunk when I was working there, tracking all this different information. It was really about maximizing the IO throughput at the disk controller level becomes your lowest bottleneck. And by having more disks available simultaneously, you get higher throughput across the entire system.
That's a lot of data.
That's a lot of data. There's a lot of cool data.
Okay, let's get past some of these extra slides. I was just gonna mention here that we have a new sync out there, and I'm gonna show that in the demo of taking Pulsar data and automatically storing that to your data warehouse and supporting some of the new lakehouse formats, including Apache Hudi, Iceberg, and Delta Lake. Today I'm gonna do Delta Lake, just because that one's new and pretty easy to work with. And it's a pretty cool format, especially if you're using Spark. So I'm going to take a look at that. What's nice is with these syncs, you set up a little YAML and add that connector there, that sync connector. And now I just have data automatically getting sent to my Delta Lake. Don't have to worry about anything. Get it into Pulsar, sync handles the rest. It's a very nice way to be able to, load data into a lake house without any kind of specialized code or any kind of special features there. And then if you want to go the other way, you can set up a source within Pulsar that will pull out of Delta Lake when things change. This is a nice feature if you want to distribute that data to someone else. So you can have data coming in and coming out, maybe getting sent to different clouds, different regions, or just getting pulled into Pulsar so it can be used for streaming analytics or combining with other streaming data sources. Makes it pretty easy, similar to the Debezium CDC use case we mentioned. I'm going to go into the demo and we're going to show how we connect and examine that data with Delta Lake. And we have hopefully everything still running. I posted the link to the source code. This shows you every step you need to do from the Python app that's getting that sensor data, then what the messages look like. Yeah, it is demo time. Hopefully nothing breaks. I've got my YAML set up right now to keep things simple so less things break. I am just pointing to a local file system. Ideally, you'd probably be pointing to S3 or ADLS2 or GCS, some cloud object store, but it also works to a file system. And this is, I have this set up for exactly once. Delta file type's going to be Parquet. And as you saw, we did that quick talk of different subscription types. I'm doing failover, so it's going to try to consume it. If something goes wrong, we'll still consume it. I created that sync based on this configuration file. I create that sync, uses this particular connector, runs in a tenant and a namespace. And we give it a name, point to the config file, says which topic I'm going to point to, set up my parallelization, get a subscription name. And yes, it is a very long line, not the, but for DevOps doesn't really matter. And I could automate that with other tools, but just to keep it simple for demos. And then once it's running in the sync, we can monitor it pretty easily from the command line interface. And I'll show you the data going into that file system, which could be an S3 bucket. We'll analyze it with Spark. We can look at the files, but they're just Parquet. And I'll show you how we connect Flink to Pulsar. It's pretty straightforward. And then we'll run it. Keep your fingers crossed. Let's see if anything timed out. This is my admin tool. Of course, that one timed out because we were gone for a while. But we're just going to keep an eye on things, see how much data is going in. I've been running that for a while now. So we'll see if things are still going on here pretty well. But data's coming in. Looks pretty good. We just got one partition here. Again, pretty transparent to you that there's partitions. Be more transparent in the future. Obviously not petabytes of data on my little demo here. Flink is still running. Spark is still running. Pulsar Summit's still running in a month. Let's go to everyone's favorite part of a demo. Seeing stuff happen at the command line, just like it's 1985. It's pretty great. Easiest way to show this though, this is that little device that I picked up and shaped and did not break. So I am just using a very simple Python app, which I'll show you that the source code is all in the GitHub. But the important thing it does, uses the Pulsar Python API to connect to a server. If it has authentication, it authenticates. When I'm connecting to my local one, so that the demo gods don't shoot me down, has no security. If I want to connect it to my cluster that I've got running on Stream Native in the cloud, I authenticate with OAuth and SSL. I connect to that topic that I passed in, so I can change that whenever I want. I'm going to use a JSON schema. And in Python, that just means I point to a very simple object here that's a record, and just define the field names, the type, and if it's required. And then give it a producer name. So if I need to track things down later, I'll know where it came from. I do my connection for my sensor, get all those nice values, put them in the record, along with some metadata that I like to have, and then send that record, set that key, and we're ready to go. And then I'm just going to return that to running. This is the admin for the Pulsar cluster. I'm just looking at this sync that we put out there for Delta Lake, make sure that records are being written to there. So we'll see new ones come in as we send them in. As you can imagine, we don't want to do one at a time, so that gets a bunch together before it batches them. And we'll take a look at that at this directory here. 117, as more data comes in, we'll get more files. And as you can see here, they're automatically generated Parquet ones. I set the default compression as snappy. There's all the Spark compression formats you could choose from. By default, pretty straightforward to do that. So as data is coming in, that'll start ramping up. We can go into a Spark console. I have the Scala one. If you look at the demo, we could also look at the Pi Spark version as well. Or we could even put that in a Python app or a Scala app or a Java app, whatever you like to do your Python. You could also do it with, there we go, got my code there. You could wrap that in another app, or if you're using Databricks, you could use their notebook, or you could use a Jupyter notebook or a Zeppelin notebook, however you do your Spark. It's pretty standard libraries. It's the Delta Lake library. Don't need anything for Pulsar. If you're want to connect from Python to Pulsar, there's a Pulsar connector out there that's supported by the Apache Spark community, as well as the Apache Pulsar community that does all that connectivity for you. So what I do here, let me show you how we set this up. It's pretty straightforward to set up. Once you have your libraries for Delta, I say I want to read a Delta Lake format, point to where that is, whether that's an S3 bucket or in my case, just a regular file system. And then I read that, and then I can get that back as a Delta table. Let me show you the schema before you show you the data. So we can look at that Parquet and it knows what those fields are. Those will look familiar. Those are the same fields we had in the JSON, the same fields that went into my Pulsar topic, and the same ones that got dumped to the Delta Lake, because I defined that schema. That schema passes along with me. So I have one idea of this data, one table, whether it's on a device, in flight, in the stream, or in my live Delta table. And we could take a look at this, and I'm just gonna take a look at that data frame that loaded up that Delta table, select a couple fields from it, order by the timestamp, show just 5 records, but give me 100 characters each so I could see it. Otherwise, it kind of squeezes it down in this ancient, very horrible format here. Not the best, but obviously with Spark, I could have another data frame that stores that somewhere else, or maybe pushes it to a Pulsar topic. Whatever you feel like doing to your data, you can do calculations, feed it to a machine learning model. You have the power of Spark here. This is about 3 minutes ago, based on what time it is now when the translation between time on my box over there. This is showing the humidity being read next to me. CO2 levels, pretty consistent. And the CPU temperature, which is a little high. But just to give you that data, and we just run it as it's coming in. This is getting fed in a pretty fast batch here as the data is coming in about not at the Splunk level of petabytes, but at a 1 row every 5 seconds, because I just have that one device. I should turn on a couple devices at once just to get more data, but just for a demo, this is pretty good. If we were in person, you'd get to point at the device and see that it's working right in front of you, but it's running here. It's coming in. We're getting more records as they come in, and then we're pushing them out to the Delta Lake. And then once those are landed in a Parquet file, we could read them as we see. This the latest ones before 39. Now we're up to 41. So we're like 2 minutes behind as it batches those together. So we're not sending, we don't want the tiniest possible files here. So we got a couple more files. And again, this could be an S3. So the latest ones at the top, they're still pretty small. Obviously, in a bigger streaming use case, you'd want these files much larger for performance. And then the Delta log there tells you where you are and updates the metadata. So when Spark reads it, it's easy to understand. That's created for you automatically by the sync. Now on the same time, we can look at this data real time. I showed you in the source code, you could take a look. We create a catalog to point to Pulsar. Then we use that, and then we could see any of the topics we've defined and have schemas as tables. And we could take a look at the table. This is the topic that we're using to feed into that Delta Lake. And we can look at that one in real time if we want to do a real-time query on it. And what's cool is once this starts, this deploys an app. Again, I can wrap this in an application and deploy it. But here I'm just running it as it comes in. And you can see here, this is running in my little Flink cluster. And as records come in, it's making them available. What we're doing right here is just displaying them on the screen, but I can insert this into another topic, or I can connect other catalogs within Flink. Flink has a bunch of different catalogs. Say I wanted to take the data I have in Pulsar and push a subset or maybe an aggregate to an existing Kafka cluster. I can create a catalog that connects to that Kafka cluster and send that data over there. The same thing with Flink. I could turn this to do most recent is what you saw here. I could have it go to the earliest available data in Pulsar, and this query can bring back everything and then add, every new record as it comes in. And then I can look at the details, and any of these fields can be sent to that next topic if I wanted, or it could go to another sync within Flink, which could be something like Kudu or HBase or Mongo or whatever Flink has a connector for. And again, or we could have done that in a Pulsar connector, just drop it there. But just gives you an idea what you could do with is our little demo, and it didn't crash. Seems pretty good to me. Basic architecture here is device. comes in. Sometimes I'll send it over MQTT, sometimes over Pulsar, sometimes over WebSockets. Can even use Kafka. Once it's into Pulsar, it doesn't matter. I pull it out any way I want. I can have Pulsar automatically sync it or tier it out to S3. Can have a web service read that over WebSockets. I'm pumping that data into Delta Lake, and I can read it with something like NiFi or a different application. You saw the data there already. Pretty easy to get access to it. It's nice. Spark, Pulsar, and Delta Lake, pushing that data around. We saw it in Flink. That's real time. Again, you're seeing SQL in two different ways. SQL against something that's stored in my lakehouse, and SQL against data that's in flight. So as that data comes in, it's getting updated continuously. So you're not, that data isn't there yet. That's why it doesn't show up. As soon as that record lands in the topic, we get that back in our query, which is great for things like fraud analytics, real-time systems, doing that real-time ETL, whatever you might want to do. We've got David, the author of the book, here with me. Is there any questions that have been delayed here?
I actually see one, Tim. So thank you for that. Great introduction. Lots of things you can do. I'm sure there'll be lots of questions. The first one was, if you insert this data into another topic, would you be modifying that topic schema? The short answer is no. I think the scenario Tim is doing, he's creating a brand new topic. So Pulsar supports topic auto creation. If the topic doesn't exist, it will create it, and it will associate whatever that schema is as the first version of that schema for that topic. Now, if there is an existing topic or existing schema associated with that topic, then there's compatibility checks. And based on how strictly you enforce that, it could be rejected. So we have support forwards and backwards compatibility on a schema basis. So if you added additional fields or dropped them and you're looking to support forwards or backwards compatibility, then those rules would apply on that.
Just wanted
Awesome,
to show
thanks.
the schema there.
Yep. In the beginning of the talk, this one's for me because I mentioned it. God, everybody wants to call me. You said there were things that Kafka did poorly that made you use Pulsar. What did Kafka do poorly that made you move to Pulsar? I will start. I will add my list. I'm sure Tim has his own, and there's some overlap between the two, but I will start since I made this comment. I think obviously some of the just to name a few again was the scalability and the forcing of people to add partitions to a topic when you first define them, because a topic is a shared resource. So there will be use cases where people wanted to have a single partition of the topic because they wanted exactly what's processing. The data has to be stored in order. And so obviously if you wanted to consume it in that manner, then it became that would be, you want to have a single partition, but another person wants to come along and consume that same data. They want to do it in a high throughput manner. They want to have concurrent reads because you can have a consumer per partition. And so they want to have pressure. They say, well, I want to have 10 or 15 or 20 partitions on this topic. So there was always a conflict about the right number of partitions to start with. If you ever had to scale up and add additional partitions because of the way the storage limitations came into play, then that became a very difficult thing to do. Again, you have to stop the entire world for that topic, block all incoming consumers and producers. While that data gets repartitioned, it has to be basically read from the beginning, rehashed based on the number of new partitions you have, and reallocated out and stored again. So that was a very, very bad approach, and that became again, speaking from a professional services standpoint, which is what I did in the field, people always complained about getting the number of partitions right. Having to add partitions was a very, very difficult thing for them. Another thing is just stability in the system. Again, there's a hotspotting in Kafka. Even if you go, there's an open source project called Cruise Control written by LinkedIn, the people who wrote Kafka, that helps them try to maintain and keep their Kafka cluster running at all times, but they just can't do it. It fails consistently. There's a lot of resiliency or a lot of issues when they have hot spotting. A broker goes down, a lot of cascading failures occur. Pulsar solves that again by having that separate compute and storage and a highly resilient system, so that if a broker dies, another one can take over immediately. You can scale them up and down. Same with brokers as well. So there were just a couple of the examples I could think of. The third being tracking your cursor position. Again, Kafka, before they replaced Zookeeper, would always have auto commits, and they would publish their cursor position using these auto commits. So they'd hit Zookeeper all the time. Every time you read a message, you're making a write to Zookeeper, which was very slow and inefficient. So I can understand why they finally took Zookeeper out. Pulsar does it differently. Zookeeper is only used to store metadata. It's interacted with once every 50,000 messages when you roll over a cursor. So it's not as abused as other systems. It became a cleaner path for utilization. So those are just a couple of the things I can mention. I'll let Tim add to that list. I could go on for a while, but I'll stop there and let Tim have a chance to talk to that point.
Yeah, I mean, we had some issues with trying to determine sizing beforehand. Very often you don't know how much data you're going to have. So some people would size it really small. Then every time you did a new app, you're adding another cluster. So I had some people I was working with that would have 200-300 clusters. Very hard to manage that because then, okay, now I got to update them. Then you're bringing down a server, bringing one up. Very hard to do that. Don't have to do that as much in Pulsar. Just being able to support those other protocols without having to put in proprietary or paid adapters or having to write code that manually pulls it out of something, does some transformation, logs into something else and pushes it along. Being able to have streaming apps and messaging and apps and front end apps and Spark and Flink talk to the same system and have one place that's the the truth for your streaming app, and not have to worry about what happens if I put too much data in there. How do I read from some legacy app, or how do I do Flink and Spark and Delta Lake and a Python app and a Rust app and a Java app and something that talks MQTT and maybe a WebSocket front end for display that's doing JavaScript or a Node.js client or a C# app. Having that flexibility, really nice, very helpful.
Yeah, I just like that. I just thought of the original reason why Pulsar was developed at Yahoo, and the use case was around georeplication. That was their first use case. So obviously Kafka existed at that point. They looked at it and realized that it had a really bad georeplication story using what do they call that thing? Data mirror, or what was the
Data Mirror 1, yeah.
Data mirror 1, where it's basically
Mirror Maker 1.
Mirror Maker 1. Thank you. It was single, so you could replicate from one cluster to another only. What they needed for Yahoo, then the use case was again the stock quote data for Yahoo Finance. So it would come in at a single feed, and they wanted to distribute it across 8 different geographical regions in real time. So have true full mesh georeplication. That was built into Pulsar on day one. That's one of the first use cases that came into play. And so that was a really good story because they'd set up Mirror Maker. If Mirror Maker dies, you're behind. You're falling behind. If you wanted to replicate to 2 different regions, you're having 2 different copies of that going on. They could get out of sync and so on and so forth. So it really became a nightmare. And that was the first driving force to say we have to write our own messaging system from scratch. Let's reimagine it from the beginning, and that's how they wrote it. And so that was just another example that came to mind. Yeah. Great question. Thank you for that question.
Well, hey, I think we have time for a couple more questions. I do want to make sure I thank our partner AI Camp, who is bringing us this awesome Zoom session here, and that brings us a lot of great talks. Want to thank our speakers, Timothy and David. Thank you so much for sharing all of your expertise here with us. And we do have time for 1 or 2 more questions if folks have them, but I do want to be respectful of everybody's time. So if folks need to leave, that's okay. There's you can follow up with Timothy and David on their Twitter feed. You can check out David's book, Apache Pulsar in Action. Yeah, and feel free to ask questions, put them in the chat channel, or take off the microphone, and now's a good time to ask.
I don't have a question, but I'd like to make a comment. I remember about 3 years ago, 2019, in July, we invited Pulsar to give the first talk at SF Big Analytics. So that was we had a video from that time, and that in that event we actually have a conference talking about Kafka, and then immediately after that I was talking Pulsar on the same event. That was interesting. So you probably can check out the two videos back then. So I'm so glad you guys are coming back for after several years doing another talk.
Yeah, thank you so much. That may have been either yes, the Stream Native days or Kafka days. We try to get around. We absolutely don't have the resources at that time, but our community is growing. That's another thing I want to stress is we recently were tagged as one of the top 10 open source Apache projects based on activity. So that's organic. That's number of commits, number of committers, number of downloads, number of stars. So really growing exponentially. We finally surpassed the number of contributors on the project relative to Kafka. So I think the momentum is behind us, but in 2019, that wasn't the case. I think, so definitely thank you for re-inviting us back and having some more opportunity to share this. Obviously, the technology's grown quite a bit and the technology's grown quite a bit, and it's just going to continue to grow. So we definitely appreciate the opportunity to talk about it again.
We're so glad you're being here.
We're glad to be here.
So are we. It's our job. We wouldn't have anything to do if you didn't invite us. So yeah, definitely want to talk about. Sorry, go ahead.
For the members, take a look. There's some ways to get started. It looks like take a look in the chat, and we'll post all these links on our meetup page as well as the recording and the slides. So if you're interested in getting started with Apache Pulsar, there's some great links.
Yep, looking forward to it. Thanks again, everyone, for attending. We appreciate your time, and thank you for the invitation. We appreciated it. Thank you so much.